Swayam Prabha. Digital India. Educated India.
So, what a natural question that some people are asking is, so what was the size of the set that we were like the theorem was being proved for? Size should be is equal to d plus 2. Does it have to be d plus 2? That is the question. Okay. So again, so let me write again version 2 equivalent again. Version 2 now, version 3 now, we already saw version 2, and we will say size of A is greater than equal to d plus 2, A is a subset of then dot 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 dot, same Radon theorem holds. Okay. Again, apparently it will look that we are doing something, proving something stronger. This theorem is being proved for what? For set of size even greater than d plus, even d for 3, d plus 4. Am I doing anything special when I say this statement? Actually not. See, if the number of point is greater than d plus 2, from this take out a set as A prime of size d plus 2. Apply the theorem, you will get what? A1 prime disjoint union A2 prime, which is equal to A prime, and that convex hull of this and this will intersect. But I want to prove it for A. So, how will I go to A? I will make A1 to be A1 prime union what? A minus A2, or A1 prime I do not have to write, I just write A2 prime. A1 is A minus A2 prime, A2 is just A2 prime. This is a superset of A1 prime, right? I know. So, convex hull satisfies an interesting, I mean, it's a very easy thing to see, but again if you go by the definition of convex hull that I have given, there is a combination. Okay. See, if A is a, so let me write, if B is a subset of C, then convex hull of B will be a subset of convex hull of C. Since I know convex hull of A1 prime, A2 prime are intersecting, and since A1 is a superset of A1 prime, then convex hull of A1 and convex hull of A2 prime, which is equal to convex hull of A2 itself, because A1, A2 prime and A2 are same, they are also intersecting. So, it does not matter, but like d plus 2 is not the only magic number, it is a threshold, true threshold, not below d plus 2 you are playing some different things happen, but from d plus 2 onwards this result holds. Okay. It's clear. So, now another natural question is, what about d d plus 1? What happens with d plus 1? Why does this result not hold for d plus 1? See, to show that d plus 2 is a critical or a threshold number is, I will build a set d plus 1, okay, for which this result does not hold, then I am done. I do not have to show it for all d plus 1 sets, by the way. Okay. This is similar to lower bounds you prove in algorithms, right? When you want to show that this algorithm or this problem has a particular lower bound, Okay. Do you show it for all inputs? Right? I will say sorting is linear, it takes linear time for all sorted lists. The list is already sorted as an input, or it is reverse sorted. Okay? Even then it is linear time, you traverse the other way. But when we say n log n lower bound, we say there are list of numbers for which it will take n log n time. I need one particular bad case and then I will be done. Okay? Okay. So, let us do it for the case r equal to 2. Let us take 3 points in like this, from a triangle. Okay. See, I can partition it into, take any two, any partition, like 2 partition, like this is set S, partition it into S1, S2, you are allowed to choose S1, S2 whatever you want, okay, but they have to be disjoint. Okay. Does the Radon's theorem hold? Whether I take this edge and this point, or I can take this edge and this point, okay, convex hull are not intersecting. Right? What happens in R3? Yes. Exactly. So, let us say the 3 points are collinear. Good. So, the 3 points are collinear. What is happening actually when 3 points are collinear? You are actually playing that game in R1. You are not playing the game in R2. So, let me give you even one more general statement, but we will do it later. Okay. Well, let us play this for with few more examples and let us see another statement. Okay. So, okay, good. So, in R3 what should you take? You should take 4 points in general position. So, general position means different things for different people. Okay. But when I say now general position, I mean that 4 points should not lie in a plane. In R3 I am playing. Okay. So, again in R3 is what we are looking at. The 4 points does not lie in a plane. By the, do not say then the 4 point, can it lie on a line? If 4 points lie on a line, then there is a plane also that containing those 4 points. Okay. Okay. So, if the 4 points lie in R3 and they are in general position, okay, can I prove Radon type theorem for this? Let us take, I take these 3 points and this point. Okay. So, let me make it black. Okay. I have taken this point and this point and this point. I will take so the convex hull of these 3 points is a triangle that is contained in the plane on which this 3 point lies, but the 4th point is outside this plane. Okay. So, you cannot do it with S1, S2 where one set is of size 1 or one set is of size 3. Okay. Because if 1 is 1, then the other has to be 3. If 1 is 3, then the other has to be 1. Okay. Okay. What about 2? Even for 2, if you see this and this, the convex hull are not intersecting. This is a very special kind of object we will be seeing. These are called simplex. We will see it later. What does it mean? Why? It will come into the, it will come in picture when we discuss Dillon triangulation. Okay. But okay, so these are simplices. Pardon? See, if I add not 4th but 5th is in R3, if I add a 5th point, I am again back to D plus 2 case. Okay. It's clear? Okay. So, let me write again and apparently a more general variant of Radon theorem, which is exactly the Radon theorem. So, this is version 4. 4, no, we have already got 3, who cares, 3. Okay. So, I say what? Yes. Okay, let us go back again. Okay, so just one second. I am not good with technology among many other things. So, okay, so tell me what. I take 4 points in R2. So, I am doing it in R2. I have 4 points. Okay. But see in R2, Radon theorem holds. I want to show why the number d plus 2 is critical. If Radon theorem holds, see in one thing you can say is, okay, if I take this convex, these 2 points and these 2 points, they are convex, what is not intersecting? That is a very natural question. Yeah. Convex hull of 2 point will be what? Segment. Segment connecting these 2 points, right? So, yeah, so for let us say for R2 case itself, let us look at the R2 case. Radon theorem does not say if you take any partition, their convex hull intersect. So, if I took this partition and this two side as a partition, their convex hull is not intersecting. What Radon theorem says is there exists a partition of the point set whose convex hull intersect. So, Radon theorem for this will be, I will take these 2 points and these 2 points and their convex hull will intersect. Yeah, it does not have to contain a point of A. No. So, see if they contain a point of A, the sets A1, S1, S2 cannot be a partition of set S. No? As a point set, it has to be partition. Okay, it's clear. Okay, good. So let us look at this another version. So I say A is a point set, finite point set. Let us call it finite. It does not matter, but finite point set in some Euclidean space. So, by Euclidean space means some d, and that d value I do not know. Okay. And now, I want to say if size of A, this means size of a number of points in A is greater than equal to dimension of the affine space of A plus 2, then dot dot dot, and like Radon theorem hold. Okay. So, when you take 3 points on a line, the affine space is R 1. So, you should apply Radon theorem for R 1. Okay. So, you can actually forget about which dimension the point set is lying. You only care about, this is what is affine dimension is one way of intrinsic linear dimension of the point set. Exactly which Euclidean space is lies. See, I mean like a line is when we say 1 flat, it lies in R3, right. So, if you have a set of many points on a line, okay, you can prove something even stronger in R3. You will not be able to speak, if the points are on a line, you will not be able to, you will get the Radon theorem for 3 points itself. You do not need 4 points for R2 case. So, this is what this theorem is saying. As again, this sounds more general, not more general. And this is something important in general, when most of the time whatever we do. So, when we do mathematics or any scientific area, you should try to understand what is the core of the hard part of the proof. Simplify it to that bare bone and understand if they prove this skeleton result, everything else will follow. The skeleton result here is d plus 2, Radon theorem for d plus 2 points, and then you can use it for getting many things. If I just give you this in the very beginning, everything will look like kind of a magical thing is happening, but with d plus 2 you can understand. Okay. So, before I end, let me take end this radon theorem part. Let us do the RD case. In RD, how should you do it? So, I am saying there is a set of d plus 1 points, okay, for which radon theorem does not hold. There is a notion of, so what you take is you take d plus 1 points in RD that are in which are affinely independent. Okay. It will define a D simplex, what is called a D simplex. Or another way to look at it is take, so let us say take D points in RD, so from P1 to PD, such that the vectors connecting origin to PD minus 1, origin to P1, okay, these D vectors, okay, are linearly independent or basis of RD. Okay. Take these D points at the origin, okay. This will be your example where the radon theorem will not hold. So, take these as the points. I need D plus 1 points, right. I have these D points plus this point. See, I purposefully did not take the axes. There is nothing magical happening about axes. Only thing you need is linear independence. That is it. Okay. Good. So, we will prove again another result which is like a very fundamental result in, so let me call it properly a theorem, Helly's theorem in convex geometry. There are different variants of it now, very strong variants, sorry, but we will prove the simplest one that itself has huge applications. Okay. Hopefully, we see one application before I end this class today. Okay. So, let me write the proper statement. Okay. Okay, right. Given, so given a collection of n greater than equal to d plus 1 convex sets in RD, if it satisfies d plus 1 property. So, I will define what is a d plus 1 property. Then, so the given collection, let us call the sets to be C1 to Cn, these are convex sets. Okay. Then we have the following result. If this collection satisfies d plus 1 property, then we have the following, not going down. Then intersection I equal to 1 to n, Ci is not equal to empty. Okay. So, I will define what is a d plus 1 property. So, let me define what is a d plus 1 property. Define d plus 1. So, rather than writing d plus 1, let us say p property of convex, collection of convex bodies. Or let me, because you are using the term p for q, let us say q property. Okay. So, let us say I have a collection of convex bodies C1 to Cn. Okay. Assume n is greater than equal to q. Okay. I will say this set of convex body satisfy q property, then any q convex bodies from the set have a non-empty intersection or have a common point. Okay. So, when do I say a family of convex bodies have q property? If I take any q of them, this are n. So, there are n choose q many q convex bodies I can take. All of them, so take any q of them, there will be a common point in these q sets. See, I am not saying that one point will belong to all of these intersections. I am not saying that. So, what does this mean? So, there are like, so take any, as I said, take any q convex bodies, there exist x such that this belongs to all of these. If you take another different q tuple, you will have also have another x prime that belongs to all of them. Right. So, this is what is defined as q property. Okay. In RD, it is d plus 1 property. Okay. That has to be satisfied. So, Helly's theorem says, if a collection of convex bodies is such that if I take any d plus 1 convex body from them, they have a non-empty intersection. Then if I intersect all of the convex bodies, okay, I have a non-empty intersection. Okay. See, this is itself is a very interesting thing, right? So, you have a collection of convex bodies, n of them, assume n is greater than or equal to d plus 1, these convex bodies are in RD. This set satisfies a particular property, it satisfies d plus 1 property. What does that mean? If I take d plus 1 convex bodies from this set, they have a non-empty intersection. Take any d plus 1, it will have a non-empty intersection. Okay. Then if this is holding, right, any d will have a non-empty intersection. Then if I intersect all of the convex bodies, see the number of convex bodies can be much more than d. It does not matter how many convex bodies you have. Okay. It can be 100 times d, 10 to the power 10 d, whatever. N has to be greater than d plus 1 basically, that is the only thing we need. Okay. Then when I intersect these convex bodies, it will have a non-empty intersection. So, there will be a point that lies in all of these n convex bodies. So, this is kind of interesting, right. Suppose I ask you to solve this problem, right. If you have an efficient algorithm for checking, so given d plus 1 convex bodies, I have an efficient algorithm for checking whether intersection of these convex bodies have some particular kind, let us say half planes or whatever. If this, I have an efficient algorithm to check that given any d plus 1, I can efficiently tell you, by efficiently I mean fast algorithms, okay, tell you whether this convex body is intersecting or not. Okay. Then it does not matter how big the n is, what will I do? I will check n choose d plus 1 tuples and I will be done with it, right. If I can find that all the n choose d plus 1 tuples are intersecting, n convex bodies, I have taken all possible d plus 1 subsets and check whether all of these convex bodies in all of these sets are intersecting or not, then I will know that how to, then I know that the original convex body, the original one, also have a collection, have a point that lies on all of them. So, I do not have to find an algorithm for like keep intersecting for n bodies. Okay. This has a very nice proof which is not possible to cover in this class, when the convex bodies are half planes, okay, while linear algebra, okay, not linear programming, basically strong duality of linear programming. This is more general. Okay. Okay. So, let us try to prove this. Okay. Okay. So, let us say we will prove it by induction on n. Okay. So, what is the base case? What is the base case? What is it? Everyone knows how to work with inductions. N equals to d plus 1, right? Right. Thing was n has to be greater than or equal to d plus 1. N equal to d plus 1, do I have to prove anything? No. D plus 1 property takes care of it. What is the induction hypothesis? Holds for n minus 1. Induction step will be holds for n. This is what we want to prove. Okay. This is to prove, and then we will be done, right? Yes. Okay. So, n is basically greater than or equal to d plus 2, right? Good. Somehow I cannot use this part properly. Anyway, so now, okay, so let us do this. So, let the convex body be again C1 to Cn. What I do is, from this original set, let us call this set S, I will build n sets. S1, Si will be basically all Cj's such that I is not equal to j. So, S1 contains all Ci's except C1, S2 contains all Ci except C2, like this. So, can we apply induction hypothesis on SIs? Yes, no? Yes. Okay. So, what do I have? So, I have a point. So, let us do that. So, there exists Pi such that Pi belongs to Pi in Rd for all I, such that Pi belongs to all convex bodies contained in Si. Okay. So, let us make this set A, which is P1 see, as a catch, remember we will apply, goal is, as I in the beginning of the last lecture I said, we will apply Radon. Radon's theorem. Oh, what is happening? Okay. For applying Radon theorem, I need a set of points of size greater than or equal to. This tells you that we have to somehow apply Radon theorem here somewhere, right? Okay. So, now do it. So, via Radon theorem, what do we know? I can partition this set A into A1, A2 such that the convex hull intersects, such that convex hull of A1 intersection convex hull of A2 is not equal to empty set. Good. Okay. So, now consider the set consider the convex set Ci. Okay. And without loss of generality, assume Pi belongs to A1. Can I assume this? Am I doing something more than what we have already done? It's just, if suppose Pi does not belong to A1, just relabel A1 to A2 and A2 to A1, then this will hold. Up till now nothing will fail in the proof, right. So, this is something I can assume. So, WLOG is like without loss of generality. Okay. Good. So, now, so observe this. Okay. So, for all Pj with I not equal to j, Pj belongs to Ci. Is this true or not true? See, the only possible point from P1 to Pn that may not belong to Ci is Pi. Otherwise, all the points belongs to Pi, by the way. Yes, no? Right? That is how we have constructed the set, right? Good. So, what does that mean? So, see, I know Pi belongs to A1, that implies all for all Pj's belonging to A2, Pj belongs to Ci. See, Pi is not in A2 because Pi is in A1. That means all the Pj's that are in A2 has to belong to has to belongs to Ci. What does that mean? You are almost finished with the proof. See, convex. So, this means the convex hull of A2 is a subset of Ci. Yes, because convex hull is the smallest convex set containing the points. Ci contains the points in A2, so it contains a convex hull. This also implies what? Convex hull of A1 intersection convex hull of A2 is also contained in Ci, and observe that this is not equal to empty, from Radon's theorem. So, what have we proved? This means this intersection belongs to is a subset of Ci. So, what does this mean? And this is true for, so I have taken an arbitrary I, right? I mean Ci I took an arbitrary Ci, and this means this intersection belongs to convex hull of A1 intersection convex hull of A2, which is a non-empty set. This belongs to all Ci for I equal to 1 to n. So, that means what? What does it mean? So, intersection of convex bodies from I equal to 1 to n is a superset of convex hull of A1 intersection convex hull of A2, because each of them contains this intersection. That is what we have proved. So, the theorem holds. So, we will like take a minute or two to see if you have any doubts. So, here the thing is, see, I mean like as the Radon theorem is the main critical thing that works. Other than that, there is a small combinatorial argument. That is it. Which Pi? No, we are not even claiming anything like that. This is, we do not care whether it contains Pi or not. See, I only have to show intersection of the convex bodies is non-empty. Whether Pi is contained or not does not matter. See, Pi, pardon, can you come again? Important thing. Okay, so let me come to this. Okay, so some issues. Okay, issues to address. What did I say? Pi may be the only point that is not contained in Ci. Pi is, it can be the case that Pi is also contained in Ci. What you know, Pi is contained in all Cj's where j is not equal to I. but even like the point that you have selected may be the one that is contained in CI also. See SI, for SI what did we need? A point Pi such that it lies in all the convex set contains in SI. I did not say find a point that lies in all the convex set that are containing in SI and should not contain in CI. This is not what we are saying. Okay, so we will do one more. This was, what was it, 2 or 3? This should be the 3 one. Caradatory theorem. This is another important object that appears everywhere in convex geometry. Okay, so let me get the statement properly and then we. So, any convex combination of a set of points A which is equal to A1 to An is a convex combination of D plus 1 points in A. This is the statement. So, why is this theorem interesting? What is the interesting feature of this theorem? Apparently, I am talking about a convex set. I am also talking about linear convex combination of something. That is how you define convex set. Why is this theorem? Why this theorem at all needs a proof? First guess, isn't it obvious? I don't say it is obvious because I know the theorem, so nothing to prove. But like, why is this needs a proof? See, how did we define a convex? So how did we define a convex combination? We said it should be something like Ci Ai I equal to 1 to n, Ci is greater than equal to 0, summation Ci is equal to 1. Right? N can be much larger than d plus 1. What this theorem is telling you is, the point may come, maybe you have generated the point by taking linear combination of many points, like convex combination of many points, but there is a representation, okay, such that if I have only taken properly selected d plus 1 points from your set, their convex combination would have given this point. It's okay. So, see, one way to prove this is via using Delaunay triangulation directly. Okay. So, let us try to prove it for d equal to 2 first. Okay. Assume these are in general position. All the general position assumptions that Arijit Bishnu was mentioning, assume it holds for this set of points also. Okay. So, you defined Delaunay triangulation, right? You have defined it. Okay. Not in terms of triangulation. Okay. So, let me vaguely define what a Delaunay triangulation looks like. Okay. What it does is, if I have some set of points in R2, let us say since we are doing it for R2, what it does is, it what is called triangulates the convex body of this set of points. It will look something like this. This S should not be present, this is a wrong, this should be something like this, or whatever. Okay. So, what it does? The term is triangulates the convex body, convex hull, the convex hull. Of the points. So, okay, so there are two ways to define convex hull. One way to define convex hull is the boundary of the convex body, smallest convex body containing the points. Here we are saying the whole convex head, like the whole, all the interior regions also. Okay. And what do I mean by triangulates? You can break it into triangles with the vertices of the triangles will be the points from your set, and it will cover the whole of your convex body, whole of your convex hull, and any two triangle will intersect at an edge or a point. There won't be intersection like this, like two triangles won't intersect like this, okay, or two triangles won't intersect like this, okay. And an edge, two edges can be disjoint, or they can intersect at one of the endpoints. So, it will look like pictorially, it will exactly look like this. This picture, if you try to formalize it properly mathematically, you will say what is called a triangulation. Okay. So, now if I know that convex hull can be triangulated like this, okay, then this theorem is one shot, right? It does not have to be unique. See, this is not unique, because if I flip this edge to this also is a triangulation. When I say flip also has a meaning, which I do not think we will be covering in this series, but there is a notion of flip also, but whatever. So, see, this is another triangulation, this is a triangulation, this is also a triangulation. One of the popular ones to use is Delaunay triangulation. There is a Delaunay, it is called Delaunay triangulation. Okay. So, let us say how to prove it, whether you can do it. Assume this is true. Assume you already know a result that Delaunay triangulation triangulates your convex body. Does this theorem in R2, let us say, okay, does this theorem needs a proof anymore? It does not, right? If a point is inside, I can write this point as a convex combination of its vertices of the triangle it is contained in. I will be done. And how many, a triangle will contain how many vertices? 3. So, it is exactly d equal to 2. So, d plus 1 is 3. So, I am done. We want to prove it without using this, basically the idea is this. And this proof via Delaunay triangulation goes for high dimension also, in general RD also. Okay. Okay, so let us try to prove this. So, let me do a setup properly. Yes, d equal to 3 you need 4 points, but no, okay. So, let us come to it. So, let us be careful slightly, okay. I said this was a proof in R2. In R3, the convex hull may be most likely will be a 3-dimensional object. The building blocks won't be triangles. See, here the building blocks are points, lines and triangles. There the building block will be point, line segments, triangles and tetrahedron, objects like these. Using this you build the triangulation. Okay. So, we will have basically a collection of tetrahedrons which intersects nicely. So, whatever that means, nicely we will formalize later, but it covers your convex, if it covers your convex hull. So, take any point now, it will lie in one of these tetrahedron, but if it is inside the tetrahedron, I know I can write it as a convex combination of this vertices of this tetrahedron, and a tetrahedron will have 4 vertices. So, I will be back to the proof, and in RD it will become what? D simplex, there is a notion of D simplex, and then you will need an object called, you will have simplexes like 0-dimensional the convex hull will be like built up using 0 dimensional simplex, which are vertices, 1 dimensional which are segments, 2 dimensional triangles, 3 dimensional tetrahedron, go up and you will get a d dimensional simplex. Okay? And you will have a collection of d dimensional simplex. The d dimensional simplex itself will cover your whole of convex hull, and then any point will lie in one of the d dimensional simplex. Again, I can write, since it is interior d dimensional simplex, I can write it as a convex combination of its vertices. So, this proof is there if you assume that result is there. We will prove it without that result. Okay? So, proof without Delaunay. Okay, so let me do a setup slightly. So, yeah, so so we want to show that for all x in the convex hull, this is true. So, let take x belonging to the convex hull of A, and let x can be written as summation convex combination of k points. First, so Ci Ai I equal to 1 to k, where Ci is greater than equal to 0 and summation Ci is equal to 1. Okay. If k is, see the set, remember your set A is A1 to An. See, if your set A is less than equal to d plus 1, like the size k is less than equal to d plus 1, do I have to prove anything? Nothing to prove. So, only interesting case is when k is greater than equal to d plus 1. Okay. Also, let us assume that out of many representations, see x may have many representations. So, let us take one example. Okay, so let me write. So, let us say this center point. Okay, so this belongs to something like this. Okay, this point I can write. So, this point is in the intersection. Let us say intersection of the diagonals of these 4 points in R2. Okay, this point I can write as a convex combination of these 3 points, as a convex combination of this point, this point, this point, or this point, this point, this point. Right? Does not have to be unique, right? But I can ask for the following thing. I will ask, use the representation that uses the least number of points. I am using AK points, A1 to AK, like k many points from the set, right? There may be many other representations also. Use the one that uses the least number of points. Okay. If I assume that, can a Ci be 0? So, let us say this be the minimal representation. Can any of the Ci's be 0? If Ci is 0, that means I can represent it with k minus 1 points basically, right? So, let us say Ck is 0. So, I can represent it with A1 to Ak minus 1. So, I can assume. So, if I am using the minimality conditions, if I assume that the representation is minimal, then all Ci's are greater than 0. So, as we have seen, the case 1, k less than equal to d plus 1, nothing to prove. Nothing to prove. What about k greater? So, now the interesting case is k greater than equal to d plus 2. So, now whenever you see d plus 2 points in RD, what is the first thing that should come in your mind? That I have enough of d dimensional geometry, but other than that, what should come to your mind? They are affinely independent, dependent, right. So, there exist di's, again not all zeros, such that summation di, where did I di ai is equal to 0, I equal to 1 to k, and summation di is equal to 0. It's okay. Okay, so now look at this d1, this d1, d2, dk. Okay. So without loss of generality, assume that dk, so WLOG, dk is greater than 0, and dk satisfies the following property. So it satisfies that among all di is greater than 0, among all di is greater than 0, Ck by dk is less than equal to Ci by di. So, among all of the di's that are greater than 0, dk also satisfies this. See, by definition, so like I can always find some di for which this equal to holds, this thing holds. I have just assumed that this is the last, the kth one satisfies this. Okay. If something in between satisfies this, flip their labels, make that ak and the other one ai, okay, and the corresponding di, ai, ci's will change. Okay. Now, look at the following thing. Ei is equal to Ci minus Ck dk di. So, I am defining some new coefficients. Okay. What can I say about these new coefficients Ei? Are they greater than equal to 0? So, the questions, natural questions, just one second, are, I am taking the, are they greater than equal to 0? Why are they greater than equal to 0? If di is negative, greater than equal to 0, right? If di is positive, then I will use this fact, I will be done. Okay. Now, consider the following object, summation ei ai. I equal to 1 to, let us say do it for I equal to 1 to k first. In this thing, what will be the coefficient of Ek? What is Ek? Ek is 0, right? Replace di with dk, cancel Ck minus Ck. Okay? So, I can basically write this. Okay? Yes? Good. I want to look at this object and I also want to understand this summation. So, we already know that Ei is greater than equal to 0, but I want to look at Ei, summation Ei is I equal to 1 to k minus 1. What will be this? This is just, I won't do it because this is just playing with plus and minus and sums. This term is equal to 1. Just replace the expression, you will get 1. Okay. And what do you get here? This is actually nothing but equal to x. So, my claim now is we have completed the proof. Why? This just play around with the equations, but suppose I can show these two things. My claim is I have completed the proof. Why? And okay, but that is not the contradiction. What was the contradiction? Pardon? Can you come again? Is that the contradiction? That is one way to prove it, by the way. Right, but I started with a statement. What was the statement? I said it is a minimal representation. Okay. So I will come to what he said. What he said is also important. What he said is, what actually have you proved? What you have proved is, if you have a representation with more than d plus 2, you can reduce it by 1. As long as it is greater than or equal to d plus 2 terms are involved in your convex combination, I can reduce it by 1. I can keep playing this game till d plus 2. When I apply it at d plus 2, I will go to d plus 1. That is one way to see this proof. Another way to see this proof is, I started with a minimal representation. That means there was no representation of x in terms of k minus 1 terms, but I found a k minus 1 term. So the minimality condition gets violated. So you can argue whichever way you like it, but both gives you the proof. Is it okay? Is it clear why what you said is also a perfectly correct way of proving it, by the way? That should be the better way of proving it. Where I was writing the proof in the morning, I should have thought about what he has done. I started with a minimal representation. Better way to think about it is, if I start with any representation that involves greater than or equal to d plus 2 points, I can keep removing one term by one term. There is a way to reduce the number of terms, but I can keep reducing it till d plus 1, because see, at one point I use affine independence property, affine dependence property. Affine dependence property I will be able to use as long as I have greater than or equal to d plus 2 points. At d plus 1 point, this itself goes, and that plays a fundamental role in the proof. So one thing you do is check these expressions. This is just playing around. If you are, but this completes the proof. Okay, I will give, what I will do next is I will give one. So you have seen one applications of Radon theorem. I will give one application. It's a very fundamental application. It's called center point theorem. Okay, of Helly's. It follows from Helly's theorem. Okay, I will give in next class. I start by proof of center point theorem, or the center point theorem statement and proof, and then I will go into incidence geometry. Okay. Did I prove this inequality? I am not even proving this inequality. What I am saying is, see, among the different di's which are greater than 0, okay, I am assuming dk is such that ck by dk is less than or equal to ci by di for all I. For all I such that di is greater than 0. See, look at all your di's, d1, okay, throw away all the ones that are for which the di is negative. Only look at the di's that are positive. Among them, I am looking at this sequence, ci, c1, so ci di. So I am looking at this number for all di greater than 0. There will be a j for which this is the minimum. The number, I can order it, right? I am assuming the minimum one is the kth one. Why am I doing it? It just looks nice. I have started with a1 to ak as if I have dropped the akth thing. If it was a j, cj dj is the smallest one among all the di's greater than 0, what would you have dropped from this expression? Aj, just to make it looks nice, you assume it to be.